note that for number 5, a particular park consists of a rectangular garden of area A and the concrete path surrounding it. So this A right here is going to be for the area of the garden. So area A for a garden. And they also tell us that we have a concrete path surrounding it. The park, so this is for the park, which I'm going to be putting in blue. The park has a total area of 1,200. So one thing is the area of the garden, which is this guy right here. And another entirely different thing is the area of the park, which is not only what surrounds it, but also what's inside. Okay, so for the area of the park, it's the path plus the garden. Well, the area of the garden is, of course, only the garden. What else do we know? We know that, for example, the width of the path at the north and south side of the park is 2 meters. So this 2 meters that is written right here is also going to be right there. Make sure that all the information they give you is actually in your diagram, because it might help you down the road for interpreting the exercise. So that 2 is up here and down there. That is information that this is giving me. And also the width of the path at the west and east side of the park is 1.5 meters. So this 1.5 right here will also be appearing over there. So we have 1.5 on the left and on the right, on the east and on the west. Yeah, the length of the park along the north and south side is x meters. So this x right here, which is cutting like that, that is what we're calling x. Well, and technically this down here is also going to be x, okay? So that might be important, you never know. And we know that these meters, or this x value, is between 3 and 300. Now, some of you probably read this and are thinking, why does this matter? And my answer to that is keep it in mind, okay? Keep it in mind that there is a restriction for the values that x can take, which actually by context, you already have one. For example, you can't have negative meters. Like x has to be greater than 0. You already have some sort of restriction. Why is this relevant? Because during our procedure, you might discover more than one answer for x, and you will end up discarding one of them and accepting one of them, given this condition here. Okay, so all that this is really doing is not here to confuse you. It's probably here to help you. If you end up with more than one value for x in one of your solutions, this will probably be the big hint for which one to accept. All right, enough blah blah. Let's jump into the exercise. For part Ai, we need to write down the length of the garden in terms of x. So the first thing I need to really leave clear to you is that when they say in terms of x, that means that your answer needs to have an x inside of it. Okay, so in terms of x means that your answer has an x somewhere in there going around. ¿Vale? So if we're trying to find the length of the garden, which I'm putting in green right here, the length of the garden is this guy right there. And so how can we express this in terms of x? Well, the red line is x, ¿cierto? So the red line is x. And so if I were to express the green line in terms of x, I can clearly say that x, for part A, I, that x minus these two ends right here, minus this end, and minus this end, has to equal green. So x minus those two ends has to give me the green, and these two ends are both worth 1.5. So for the area, or sorry, for the length of the garden, x minus 2 times 1.5 will give you the length that we're drawing in dark green. Okay? So x minus 3 has to be the length of the garden, which I'm putting in this green line. ¿Vale? So I'm putting the green line to replicate this green line. If you want to get more fancy, you can just, maybe write here length garden. Okay? Just so that you don't forget. So length of the garden has to be x minus 3. a very visual solution in this case, and that is why I suggest that all information they give you to actually put it into your diagram. It makes it a lot easier to see the procedure you have to follow. Yeah, so for part Aiii, my final answer is simply going to be x minus 3. And I'm going to put it in light blue so that we recall that this is the answer. Then for part Aiii, we have that we need to find an expression for the width of the garden in terms of x. So for the width of the garden, well, we just found the length of the garden. So now we have to find the width of the garden. See? Well, just to make this diagram a little bit more complete, technically up here we have an x minus 3. And for the length of the garden, well, how can I try to find that from here? All right, so you have the length of the garden, you're trying to find the width of the garden, but you don't have the area of the garden yet. And so if we try to solve this directly thinking of what you have in regards to the garden, you're not going to be able to solve it. You have to go above and beyond. And in this case, think about it this way. This line in purple, if you connect it to something else, what does it turn into? This line in purple, technically you can connect it like this, boom, which is the same as if I were to draw this line here. And so technically this line in purple that I put earlier for the width of the garden does have to do with the width, it does have to do with the width of the park. Technically, the width of the park is going to be 2 plus purple, right? Plus 2. And so width of the park, we now know is 2 plus 2 plus the width of the garden, which is the purple line. See? Just so that we're all on the same page, let me erase what's in pink because it might be a little bit confusing. The width of the park, so this whole section here, right, has to be 2 plus 2 plus the line that I'm putting in purple right there. Okay? So the width of the park, of course, has to be 4 plus the line in purple. Yeah? And just so that we all sort of maybe keep this clean, we're going to call the line in purple y. Okay, so the width of the park has to be 4 plus that y. Yeah, so how can I try to find y? Because at the end of the day, we need to find an expression for the width of the garden, which we're not calling y, in terms of x. So you want to reach y equals something something x. Dale? All right, so the width of the park, what do you know about it? How can you work with it? Well, you know that the width of the park times the length of the park, which is x, ¿cierto? So the width of the park times the length of the park has to give you 1,200 because the total area of the park is 1,200. So notice the procedure. You went piece by piece. Could you find the value for y just with the garden? No, because you don't have the area of the garden. Do you have the area of the park? You do. Can you put y into your formula for area of the park? You can, but you end up with a bunch of x's. Do you care? You don't care. Actually, you're happy because you want to leave it in terms of x. So from here, what you do is say, okay, the area of the park is 1,200. So for part A, double that, you will say that 1,200, the area of the park, has to equal the length of the park, x, times the width of the park, 4 plus y. And from here, you need to get y alone. Now, I guess there's a couple ways to solve this. I don't know what's the quickest way. Well, the most intuitive way for me, at least, is first you distribute. Okay, so if first you distribute, you end up with 1,200 equals 4x plus xy. So you want to get y alone, ¿cierto? Width of the garden in terms of x, so y equals something something x. You can go ahead and do minus 4x minus 4x. So xy has to equal 1,200 minus 4x. From here, you can divide by x to both sides. When you divide on the right side, you have to divide everything by x. You got to be consistent. So y equals 1,200 divided by x. minus 4. So bada bim, bada boom. I put it in blue because it's my answer. The expression of the width of the garden, which we did call y in purple. So we did call it y in purple. So y equals 1,200 divided by x minus, this is a 4. Okay, no one should get confused. This is a 4. Okay, and if we check the answer key real quick, there it is. Okay, so y equals 1,200 divided by x minus 4. See? Yeah. All right, and last but not least, for part A triple I, they tell us hence, this is a very important word, show that A equals all of this. Yeah, first things first, when they talk about hence, it means, it's kind of like saying therefore. Okay, so given that you solved AI, and given that you solved a double I, find me this. And so hence is a very, very, very big and awesome hint that, hey, you gotta use what you found out earlier to show me this. Okay, so in terms of procedure, it can be a very, very big hint. So how in the heavens does finding the length of the garden and finding the width of the garden help me to find big A? Well, the first question you should be asking yourself is, what the heck is big A? So you scroll back up. Well, in your case, you're going to look back up because you have the paper in front of you. And you say, okay, what is big A? Big A is the area of the garden. And so the garden is indeed a rectangle. And so for rectangle, you just do length times width. This is pretty much common knowledge at this point. And so the length times width of the garden, as you see here, is the line in green, x minus 3, and the line in purple, y. Now you know that y is this, ¿cierto? So technically for part A triple I, it says show that big A equals this, ¿cierto? So really you just have to calculate big A yourself. So big A, we know, is area of the garden. And so for the area of the garden, you have to do length times width. And you know by context, or by what we figured out so far, that length is going to be this x minus 3 that's in green, while the width is going to be what we have in purple, the y. Now from part A double I, you found that y is actually going to be this right here, 1,200 divided by x minus 4. So this y turned into this here from part A double I. So notice how the hence or the thus or etc. is helping a lot with this part of the exercise. Actually, this part here is from part A single I. See, from part AI. And so I'm just insisting on the point when they say hence, it's a big, big hint for how to move forward. Literally in this part, you have to use, for part AI, you found x minus 3, and from part A double I, you found the value for y, okay? So when they say hence, it's a big hint, okay? Use it to your favor. All right, from here, we need to reach these numbers. We need to reach the 1212, the minus 4x, the minus 3,600. We have to figure out how to get there, see? And so the first thing we can observe is that there are no parentheses. So clearly, you gotta get rid of the parentheses, ¿vale? Whenever you have two parentheses like this, next to each other, all you have to do is multiply the first one times the first one times the second one, and then multiply the second times the first and the second times the second. Pretty classic. You should have seen it in class, by now, but what you end up with is that big A equals, well, this first multiplication is going to be x times 1,200 divided by x minus 4 times x, and then down here you end up with minus 3 times 1,200 divided by x, so negative 3 times negative 4, you immediately end up with plus 12. See? So from here, what can I sort of solve right away? Well, this will go away with this, ¿cierto? So there you end up with only 1,200. This is just going to turn into 4x. This is going to turn into 3,600. And this 12 with this 1,200 will end up, will add together as 1212. So at the end of the day, once you do all of that, combining like terms, etc., you end up with the 1212 minus 4x minus 3,600 divided by x. And so there, bada bim, bada boom, we have proven, or we have shown, that big A equals exactly that. You double check your answers, it looks well aligned, checks out to me. There you go with part A. Later on, they tell us for part B that we need to find the possible dimensions of the park if the area of the garden is 800 meters. So area of garden, what do you know for area of garden? Area of garden, you know that it's this right here. Okay? So what are the possible dimensions of the park? Yeah, when they talk about dimensions of the park, they're talking about the length of park and the width of park. Dale? So first things first, we're gonna need a lot more space for this. So length park, we know is, length park, we know is simply x. While the width of the park, so width park, is 4 plus y. Now we also know that y is this guy right here. So if you do 4 plus y, you end up with 4 plus 1,200 divided by x minus 4. So really for the width of the park, you're just going to end up with 1,200 divided by x. 1,200 divided by x. Yeah, so that's the length of the park. That's the width of the park. And over here, they tell us that the area of the garden has to be 800 meters. So think about it this way. Area of the garden is 1212 minus 4x, and then I think it was another minus. Yes, minus 3,600 divided by x. So really what's happening here is that they're telling you, yo, if the area of the garden is 800, this obviously has an impact in your value for x. So given the values of x that you're about to discover, okay, given the values of x you're about to discover, plug that value of x over to length and over to width and tell me how big it is. That's what it's asking for. It's telling you, find the possible dimension of the park. So find the length, find the width, if the area of the garden is 800. Now, if the area of the garden is 800, I'm plugging in 800 right here. That means I can get a value for x, and whichever value of x you find, you plug it in for length and width, and that will be your answer. So the big sort of challenge right now is that you need to solve what I'm putting in pink right now. And so how the heck do you solve that, right? Okay, there's two main ways in which you can try to solve it. See? So on the one hand, and I'm going to show you both because I think it's important to have as many tools as possible. Okay? So on the one hand, what is annoying you right now? Right now, you're probably annoyed by the fact that you have an x in the denominator. So how do you get rid of an x in the denominator? What you can do is multiply everything by x. So if you multiply everything by x, you end up with 800x equals 1212x minus 4x squared. And over here, sorry about that. And over here, you have 3,600 divided by x times x. But if you have divided by x and times x right next to each other, then boom, boom, you only end up with 3,600. So, oh, look at that. From here, maybe it turns out to be easier to solve than what you think. So from here, you want to get everything onto one side because this should be looking familiar. This should be looking a little bit like a parabola. So try to get it into the parabola equaling 0. So I'm going to go ahead and throw everything to the side on the left. That is, so if I throw everything to the side on the left, I would be doing plus 4x squared to both sides. I would also be doing minus 12x to both sides. And I would also be doing plus 3,600 to both sides. So if you do all of that at once, trust me, what you're going to end up with is, on the one hand, you end up with 4x squared. You also end up with minus, how much is that actually? 412x, ¿cierto? And also you end up with plus 3,600 equaling 0. Now, because all of these are even, I could technically divide everything by 2. So that's just something to make this a little bit more simple. So if I were to divide everything by 2, and that's just a big hint you can always use, ¿cierto? If it equals 0, dividing this by 2 still keeps it at 0. So this is just to make the numbers more friendly looking, right? So you can divide everything, for example, by 2, right? So if you go ahead and divide everything by 2, what you are going to end up with is 2x squared minus 206x plus 1800. And look at that, they're still all even. So I can again divide by 2, again divide by 2. So x squared minus 103x plus 900 equals 0. And from here, you've probably been here a million times. You have to solve for x, you have to solve for the parabola when it equals to 0. So there's a couple different choices you can take from here. The classic is maybe factoring. And so factoring is when you end up with 2 parentheses, right? It's usually like, I don't know, x plus 2, x minus 3, something like that. You can also do the quadratic formula, okay, which is in your formula booklet, which would be, just to show you the tools, formula booklet is, I'm pretty sure it's in here. I'd be surprised if it's not, I'll be honest. I'm pretty sure it's here. Quadratic function. Dude, no way it's not here. Quadratic, there it is. Yeah, so solutions for a quadratic equation, you can technically use this right here. Okay? Yeah. So that works, that's another option. But a lot of you are probably used to is simply graphing. Okay, so if you go ahead and graph this, you can find where x equals 0 because you do have it equal to 0. See? So you can go to y equals, make sure it's all clean, you put x squared minus 103x plus 900. Then you're going to go ahead and graph and try to find the values of x from here. Now it's very likely that your window is very different and you can't see it well and stuff like that. So here I can barely see it, which is probably your scenario as well, or maybe your scenario you can't even see it. So what you're going to do, or what I suggest, is that you press zoom, scroll all the way down and press zoom fit. So once you press zoom fit, this usually helps you see the intersects. Now this might help you see the y-intercept instead of the x-intercept. Here I see one of the x-intercepts, but there might be another one because this is a parabola after all. However, pressing zoom fit can give you a better idea of how to change the window. So for example, all these negative x values, well, you don't really care about them because actually they tell you earlier that x has to be between 3 and 300. So immediately you can already say, oh, okay, so my minimum x we can leave it as 0 and my x maximum we can leave it as 310. Yeah, so that's the first thing we can do. Y max probably doesn't need to be that big. You only care about the x-intercepts. Just to leave it more pretty, I'm going to put minus 10. And y max, we're going to say whatever. I don't know, like 100. ¿Vale? So now we graph. Doesn't look particularly pretty, but I can see both x-intercepts, which is what I actually care about. See? So you can go ahead and press second and then trace in order to hit calc. We are calculating zeros. zeros is for x-intercept. So now it asks for left bound and right bound. Make sure you find where your point is. So there it is. Let me go all the way to the left first. Yeah, so here we have for left bound, right? Then we press somewhere on the right, no one cares where. And so notice, there in my graph, we have two dotted lines. Your graph might not show it, but it's still going to ask for the left and right bound. And so what the left and right bound does is that it's going to scan within these bounds where in your function you have a 0, where in your function you have an x-intercept. And so the guess, it's not because your calculator is dumb, it's because in case your bounds had more than one x-intercept, this guess would allow you to choose which. Okay, but I'm going to press enter around here, and x has to equal 9.64. We can, significant figures, we can just leave it as 9.64, honestly. So this is one of the x values that I'm getting. The other x value that you can get from over here, if again I do calc 0, go all the way to the right, and then make sure my left bound and right bound is correct. All right, so there's good enough. That's my other x value. So 93.35. You think in terms of significant figures, I'll just show you quick. 93.35. If you think in terms of significant figures, it would be 1, 2, 3. Round it up or keep it the same. You round it up. So significant figures here would be 9.34. Sorry, 93. I'm trolling. 93.34. Ah, I can't math. 93.4. All right, awesome. So these are the two values of x that you get from here, right? So that's one way to solve it. Of course, you could have used quadratic formula and a bunch of different stuff. The other way to solve it, in case it's easier for you, I'd rather show you, is using the calc intersect trick. If you're good enough with this explanation, you can probably skip ahead in the video, but I will show you one more tool. So your other tool is calling this, let me use another color, is calling this y1 and then calling this y2. And so if you call that y1, so 800 will be y1, and y2 will be this guy here, the 1212 minus 4x minus 3600 divided by x. If you go ahead and graph this, well, then I can change the window immediately because I sort of know the answer already. I know that x ends up being those values here. I know that one of my y's is 800, so I'm going to put a y max of 900. If you go ahead and graph from here, you're going to get two intersects. Now notice, why do I care about intersects here? Because these two equations, the y1 and the y2, what are they doing to each other? They are equaling each other. So wherever two lines are equal is where they intersect. So, the other trick is using calc intersect. If you use calc intersect here and call this y1 and call this y2, you can go second, trace, enter to hit calc, go to intersect instead, pick your first curve. Make sure it's your first curve because sometimes people press down or upwards and they skip. I mean, they jump from one to the other. So your first curve is going to be the flat one. The second curve is going to be the red one. Go ahead and press guess nearest to the first one you want. And there you go. You got the same answer, the 93.35, which we left as 93.4. And for the other x value, again, you press the blue one as the first, or the flat one as the first, and then the red line as the second, ¿cierto? And then the guess near the one we want now, 9.64. So both solutions work. Do whichever one is easier for you to understand. Okay, for me, I love the calc intersect trick, but I know that is not everyone's bread. Okay, so to each their own, whatever floats your boat. Here are the values for x. Now we're not exactly done yet because here it did say, and never forget, to find the possible dimensions of the park, if the area of the garden is 800. So you got two values for x, ¿cierto? You got a 9.64 and a 93.4. And so technically, my only condition for x is that it has to be between 3 and 300. Both of them fulfill that. So this is a little bit more of an annoying sort of exercise, but I guess what we should be answering here are the two different lengths and the two different widths we can get. So on the one hand, using light green, so light green for this scenario, okay? So on the one hand, you can have a length of 9.64 and a width, this is in meters, right? Yeah. So on the one hand, you can have the scenario of 9.64 meters for length and the width of 1,200 divided by 9.64. And the width of significant figures, you can leave it as 124. Yeah. 124 meters. So that's the first scenario, ¿cierto? A length of 9.64, a width of 124, or the scenario in dark green, which is with the other value of x. The scenario in dark green would be the length of 93.4 meters and the width of 1,200 divided by 93.4, which would give you a width of 12.84. And in terms of significant figures, it's 12.8 meters. So these are your two scenarios for length and width. You either have a length of 93.4 with a width of 12.8, or, let me leave clear that this is a decimal, see, 12.8. Or you end up with a scenario of 9.64 length and 124 width. If we check the answers over here, you can see both scenarios, right? So on the one hand, you have the 9.64 or the 93.4. And so one of the scenarios for width is 124 or the 12.9, ¿cierto? So as long as you express both scenarios, you're gonna be good to go. I know here I put 12.8. That's only because I was using significant figures. As long as you're consistent in your procedure, you're still gonna get full points, ¿cierto? In fact, here it says accept 12.8 for the second value, right? That's because you're using three significant values. So as long as you're consistent with the significant values in your procedure, everything will be okay. So trust me on that, all good, no worries. Yeah. And then we have the hard part for part C. Maybe even why you clicked on this video. So for part C, we need to find an expression for that. What the heck even is that? See, this, you guys, is the derivative. Derivative of a in respect to x. So you take this equation here and you will do the derivative in respect to x. There's two main things I have to go over. The first one is derivatives, of course. But the second thing I have to go over is that, notice, for part C, you need nothing from part B and even nothing from part A. Because this because this show that is telling you that this information is true. It's like, I don't know, show me that the earth is round or something like that. See? We know that it's round, you just have to prove it. So you can, in other experiments, use the fact that the earth is round to your advantage. This is the same scenario. For part C, you need to do the derivative of a in respect to x. Well, you already have the derivative. You already have function a in terms of x. So you can actually already do it because you know that this information is true. Why do I mention this? If the day of the test you are running low on time and you need to claw for points, search for phrases that say show that. Because that might allow you to skip ahead and do something like part C. I'm just saying, that's the kind of stuff that might give you the extra edge you need the day of the test. Anyways, from here, we simply need to do the derivative of that equation. ¿Cierto? So that equation is, a equals 1212 minus 4x minus 3600 divided by x. Dale? Now, if I go ahead and open up the formula booklet and I look up derivative, here it is, ¿cierto? So the derivative of an exponent is the classic. For me, it's much more well understood if I just give examples. So for example, if you have x squared, the derivative of this is 2x. If you have x cubed, the derivative of this is 3x squared. This is consistent with the formula. Notice, focus on the n. What is happening to the exponent? On the one hand, it's going to go down in front, multiplying. And on the other hand, it's going to get a -1 up top. So for example, the in-between step that's happening here is that you end up with, well, this is going to go in front. It's going to be 2x. And on the exponent, you do 2 minus 1. And so 2 minus 1 means you end up with a 1 on the exponent. ¿Dale? The in-between step over here is that this 3 goes down in front multiplying. So you end up with 3x to the power of 3 minus 1. 3 minus 1 is 2. There you go. All right, that's the in-between step. It's all that's really happening. It's two things. The exponent multiplies in front, and the exponent gets a -1. Now, the interesting scenario, which is what they throw us immediately, is when the x is below, ¿cierto? So when the x is in the denominator, how does this work as an exponent? Guys, that's the other thing I have to explain very quickly. Technically, I guess I'm going to... it's a classic, I always show it. You can skip ahead if you already know, but basically 2 squared is 2 times 2, which is 4. 2 to the power of 1 is 2, which is 2, and 2 to the power of 0 is 1. And 2 to the power of -1 is 1 over 2, and 2 to the power of -2 is 1 over 2 times 2, in other words, 1 over 4. So notice, there's a certain pattern here that is clearly arising. When you want to go up, all you have to do is multiply by 2. And when you want to go down, all you have to do is divide by 2. And so there's two main things that we're learning here. On the one hand, when you have a negative exponent, ¿cierto? It means that you sort of have to like flip it. Okay, that's what I need you to get into your brain. If you have, for example, 2 to the power of -2, first you flip it, and then you do the exponent. That is what I mean by flip it, okay? So that's one thing we can learn from this example I just gave. And the other thing you can learn is that, notice, this 4, when you divide by 2, you go from 2 squared to 2 to the power of 1, ¿cierto? And this 2 to the power of 1, if you divide it again, you end up with 2 to the power of 0. And here you're doing 2 divided by 2 equaling 1. And that is why, with what I'm putting in pink here, this 2 divided by 2 equals 1. That is why anything to the power of 0 has to equal 1, because eventually you will do itself divided by itself, and itself divided by itself has to equal 1. This is a pattern that happens everywhere. 3 cubed is 27, 3 squared is 9, 3 to the power of 1 is 3, and eventually you face the same problem or the same pattern, ¿cierto? Here you divide by 3, here you divide by 3, 3 divided by 3 equals 1. So, two main things we learned. Anything to the power of 0 has to equal 1, and for negative exponents, you will be flipping it as shown right here, ¿cierto? Now, this also applies in the other direction, okay? What do I mean by this? Before doing the derivative, make sure you get the exponent in the denominator out of there, ¿cierto? So because a negative exponent means that you flip it, well, if you want to flip it from here, you can actually go the other way. So flipping it from here means you end up with x to the power of -1. Because x, and this is the big brain play, see? X to the power of -1 is 1 over x. X to the power of -2 is 1 over x squared. Ah, that makes a little bit more sense, doesn't it? And so right now, we just had a 1 over x. We want to be able to see the exponent so that we can do the derivative of an exponent more easily, ¿cierto? For the derivative of an exponent, it's easier if it's up top. So this is what we're applying right now, ¿cierto? You want to get rid of the x in the denominator. You want to put it up top. But because it's in the denominator and you're flipping it, the moment you flip it, you're putting a negative exponent. So this is the equation for area simply rewritten. Okay, all you really switched around was this guy here converted to this guy here. That's all you did. Everything else is the same. And from here, sorry, we can do the derivative of an exponent. So from here you do the derivative, and from here you realize, well, this 1212 doesn't have an x, so this 1212, boom, disappears. This minus 4x, you have an x to the power of 1, so this is going to be 1 times negative 4. So minus 4 times 1 times x to the power of 1 minus 1, ¿cierto? Following the rule of, first of all, the exponent multiplies in front, and second of all, you do a minus 1 to the exponent. Minus 3,600 times negative 1, because it's this exponent here, ¿cierto? Going in front, times x to the power of negative 1 minus 1. And so from here, what you end up with, clearly, this ends up as x to the power of 0, and anything to the power of 0 equals 1. We learned that a second ago, so you end up with minus 4. Here you have a negative times a negative, so it actually ends up as plus 3,600 times x to the power of negative 2. So if you were to rewrite this and leave it a little more pretty, if you'd like to, you can leave it as 3,600 divided by x squared minus 4. That would be for part C. Just so that you all believe me, there it is. All right. And so for part D, it literally says use your answer from part C, okay, to find the value of x that will maximize the area of the garden. And so here, there's a quick sort of hint that I have to give you, okay? Guys, whenever you want to maximize or minimize something, or even more generalized, whenever you want to optimize something, you have to ask ChatGPT. Nah, just kidding. Although that is kind of true. Whenever you want to optimize something in math, and when I say optimize, I mean that you either, for example, maximize, I don't know, benefits, maximize area, or minimize costs. All you have to do is take your derivative and equal it to 0. And I'm going to have a quick 1 or 2 minute explanation of why you have your derivative equal to 0. But for now, you can go ahead and jump to the solution, which is, okay, so that means my derivative has to equal 0. That means I need to find 0 equals 3,600 divided by x squared minus 4. So you can go ahead and start solving for now. I will explain, however, why you have your derivative equal to 0, because oftentimes I see that people don't know, and you're here to learn, right? You're here to learn, I suppose. So the explanation that is probably not going to be that quick, but I'm going to try, is the following. Let's say you have a parabola, see? So a function that looks a little bit like this. The thing I'm putting in red right here. Got it? In its original version, let's say it's x squared plus, I don't know, 3x plus 2. I'm just making it up. I don't think it actually looks like this. I'm just making it up on the spot. Got it? If you have something that looks like this, if you were to plug in an x, you would get a y. For example, if you plug in an x of 0, boom, boom, you end up with a y of 2. If you plug in an x of 1, you end up with 1 plus 3 plus 2, you end up with 6, ¿cierto? And so if this is the main idea, in the original, right, so in the original, if you haven't done the derivative, if you haven't done the integral, if you haven't done anything at all, this that you're getting right here are sets of points. Whoops. Yeah, it's 0, 2. It's 1, 6. They're all like x, y coordinates. Yeah. The main idea is that when you do the derivative, which if I were to do it right now, you end up with 2x plus 3. Okay? When you have the derivative, it's not exactly sets of points anymore. Dale? I mean, this x is giving you an x coordinate and the y coordinate that you graph onto your graph, of course. But now, what you're asking is a little bit different. See, for example, if you plug in an x of 0 here, your y ends up as 3. If you plug in an x of 1, your y ends up as 5. And this is actually a little bit different, see? Because although you can also say that, okay, this is also like an xy coordinate, ¿cierto? This is also, like, I just found the point 0,3, I just found the point 1,5, but the context is different because the context is that of a derivative. The main idea is that in the original, basically you are asking your function, when x is this, what is my y at that point? Instead, in the derivative version, you're saying, when x is this, what is not your y, what is my slope? When you do the derivative, it actually helps you find the slope. So in the original, when x is 0, y is 2. When x is 1, y is 6. In the derivative version, when x is 0, my slope is 3. When x is 1, my slope is 5. So, that makes a little bit more sense. And actually, if I were to graph this very quickly, just so that we're all on the same page, I think it's important for us to understand this explanation, because I wish someone told it to me back in my day, but, well, at least I'm here to tell you now. We go ahead and do maybe zoom standard would be fine. So notice, you end up with something that looks a little bit like this. Okay, so what you discovered from the original, which I'm putting now in red, so from the original, you discovered that when x is 0, y is 2. You discovered that when x is 1, y is 6. So you ended up with something that looks a little bit like that, ¿cierto? But in pink, the derivative, it's basically, when x is 0, the slope is 3. When x is 1, the slope is even greater, the slope is 5. So notice, it's a little bit different, the information it's giving you. Now, following the idea of the slopes, because I did say you have to have your derivative equal to 0, ¿cierto? Now, why do you have your derivative equal to 0? Because, well, if your derivative equals to 0, I'm saying that your slope is 0, ¿cierto? So basically, you're working backwards. You're saying, okay, if my slope is 0, what is my x? That's what you're saying. So if your slope is 0, well, where is your slope 0 in a parabola? Over here, you have a slope of 5, because you discovered it there. Over here, you have a slope of 3, because you discovered it there. And if you keep going, here is like a slope of 1. And here, ladies and gentlemen, you have a slope of, there is your slope of 0. And so if you plug this into your derivative function, you're saying, when my slope is 0, what is my x? And even in this same example, when my slope, so this entire thing, ¿cierto? This y, when my slope is 0, what is x? So 0 equals 2x plus 3. That means that 2x equals negative 3. X equals negative 3 divided by 2. So that means that at this point here, you have negative 3 divided by 2 for x, ¿cierto? So x equals negative 3 divided by 2 right at that minimum point. See? And so, notice, the main idea, or what's happening here, is that at the min or max, your slope is 0. And so if you take the derivative and you equal it to 0, you will successfully be asking your derivative function, yo, when my slope is 0, what is my x? And you know that when your slope is 0, you will be at the minimum or maximum. And so what you know of the minimum or maximum right now is that it lies at negative 3 divided by 2. All right, so if I apply that down here, it's the same idea, okay? So you took your derivative, you equaled it to 0 in order to find the value of x. You're also finding the value of x up here. You discovered it was negative 3 divided by 2. You will be doing the same thing down there, ¿cierto? So from here, you need to get x alone. There's a couple different ways. You can use y1, y2. It's a trick that works. For me, I see a relatively more cool way to solve it. And the cooler way is that, you have an exponent in the denominator. Nobody likes that. Multiply everything by x squared. So if you multiply everything by x squared, this goes away with this. And you will end up with, well, 0 times x squared is still 0. 3,600 remains by itself. And the 4 is multiplied by x squared. So from here, get x alone. So you can do plus 4x squared, plus 4x squared. So 4x squared equals 3,600. You can divide both sides by 4 in order to get x alone. So x squared has to equal, I think that's 900. Yep, it's 900. And from here, you gotta do square root to both sides in order to have this go away with this. So x has to equal plus or minus, because it is square root, plus or minus square root of 900. 30. Sorry, plus or minus 30 like this. See? In case you're confused by the plus or minus, yet another quick explanation, is that when you find the square root of something, so you're basically asking, in terms of math, which number multiplied by itself gives me what's inside. Which number multiplied by itself gives me what's inside. So you can do 30 times 30 gives you that 900, but you can also do negative 30 times negative 30, and that also gives you 900. So that is why for solutions with square root with a base of 2, you always leave your answer as plus or minus 30. However, in this context, ta-da! I told you it was going to be relevant. X has to be between 3 and 300. So between x being negative 30 and x being 30, clearly you end up with the choice of x being equal to 30. So here we can change the plus or minus to simply be x equaling 30. So that would be for part D. And last but not least, we need to find the maximum possible area of the garden. Well, we know that at x equals 30, we have our optimal point, ¿cierto? For maximizing the area. Now we have to find the actual area. And so the area formula is right here. It's the one we've been using all along. So all you have to do is plug in 30 into that. So you do 1212 times 4 times 30. Oh, I just rolled. 1212 minus 4 times x, which we will be calling 30, minus 3,600. You put the fraction using alpha y equals, then pressing the first. 3,600 divided by 30. You check your work. It's asking for area of garden. This is for the area of the garden. That should be fine. So I'm going to go ahead and press enter. Just checking one more time. It's good habit. You press enter, 972. So for part E, all you did was plug in 30 into your equation for area. So you ended up plugging in 1212 minus 4 times 30 minus 3,600 divided by 30. All right, did run a little bit out of space near the end, but hey, that was an intense problem. I think we earned it. See? So don't forget your units, meters squared. I show you the answer key so that you keep believing me, even though I always put it at the end. Here you have the x equals 30, and here you have the 972 meters squared. Ladies and gentlemen, number 5 was pretty intense. Number 5 was pretty intense, but I think we had a pretty good explanation of how derivatives worked. We learned more than one thing today, and that's the idea. I hope it helped. That is for number 5, and that is for the entire paper. See you around.